everyone, my name is Rahel Amentie. I came from Addis Ababa University and my specialization is environmental geology and geohazard stream. My supervisors are Professor Gazahan Yirgu and Dr. Biniam Tasfa. And my thesis title says Volcanic Hazard and Risk Assessment from Future Eruptions of Fentale Volcano, Northern Main Ethiopian Rift. These are the outlines: introduction, material and method, geology of Fentale Volcano, and the surrounding region, results and discussion, conclusion and recommendation. I will start the presentation by defining what volcano means. Volcano is a vent, or it is an opening in the surface which allows the entrance of hot earth materials such as magma, hot gases and rock fragments to raise out into the surface. And those hot earth materials or magmas are stored within a large reservoir, so-called a magma chamber. So when they get an entry or an entrance, such as a ruptured surface, they raise it out into surface. And when they flow as a thin flow, which is called a lava flow, and when the viscous magma raised out into surface, which will form an eruption column, and when it collapses due to gravity, it will flow, and it's so-called pyroclastic flow. And when the pyroclastic column collapses, it falls as ashfall deposit. There is a volcanic hazard which is associated with a volcanic eruption, and it is so defined as the probability of volcanic eruption occurring at a given geographic area within a given period of time. And there are any factors which are associated with volcanic hazard, so-called volcanic risk. So volcanic risk is defined as unexpected amount of loss or property damage which are caused by volcanic hazards. There are different volcanic activities in the world, and East African Rift System is a well-known area having different active volcanoes inside. And there are two main segments in East African Rift System, such as Main Ethiopian Rift and Afar Rift, and where there are different active volcanoes took place. Study area description. The study area is located in East Shoa zone of Oromia regional state, North Shoa zone of Amhara, and South Afar region. And the whole area covers about 1,690 kilometers square, and it is far from Adama town by 96 kilometers and from Addis Ababa by 200 kilometers. There are different exposures in the study area, especially Awash National Park surrounds the Fentale caldera. This is the boundary of Awash National Park. And when we come to the south of Fentale caldera, there is a lake, so-called Lake Basaka, and the main two towns in the study area, such as Metahara and Addis Katama, are here. And also there is Awash River, which is located in the southern eastern end of the study area. Statement of the problem. Volcanic hazard has different impacts in both living and different man-made activities. Many peoples in the world live around active volcanoes because of different resources which are generated from volcanoes, such as soil fertility, physiography, attraction, and also there are different geothermal features such as hot spring system in the area. So the area is surrounded by different economic activities, such as there is sugar plantation and Awash Malka farm land in the area, and also there is Awash National Park. So they are main for the key development of the country. And there is also infrastructural development. There is a railway which connects Addis Ababa from Djibouti in the area. And also there is a Matara sugar plantation. So those vulnerable or exposure will be harmed due to the eruption which is occurred during future. So the main purpose of this study is to assess the volcanic hazards on those exposures and in order to assess the volcanic risk from future eruption. Objectives. The main objective of the study is assessing and mapping the volcanic hazard and risk of the future eruption in the Fentale volcano. And there are different specific objectives, including reconstructing the past eruption history of the area in terms of geology and stratigraphy, identifying different magmatic vents and geothermal features such as fumaroles, hot springs, and mud pools in the area, preparing the volcanic hazard map of the area using satellite imagery, specifically Sentinel-2A image, and assessing the vulnerability and exposure of the area, such as populations, infrastructure, land use, land cover, different facilities such as health facility, religious facility, and preparing the volcanic hazard and risk map of the area. Materials and methods. Different materials were used for the study purpose, such as primary and secondary data. Field data and satellite imagery are among the primary data of the study. Field data were investigated for identifying different volcanic products in the study area and for identifying different geothermal features in the area, because those geothermal features are a good sign of volcanic unrest, and they indicate the presence of eruption in the future. And satellite imagery, so-called Sentinel-2A, was downloaded from the website so-called Copernicus Open Access Hub. The DAM, having 12.5 resolution, was downloaded from Alaska Satellite Facility. Tabular population data was acquired from Central Statistical Agency of Ethiopia. Geologic map from Geological Survey of Ethiopia, and spatial population data was downloaded from DIVA GIS. And basically, remote sensing and GIS method was applied in this study. Satellite image interpretation was conducted for generating different geological features for assessing the lava flow hazards, such as fault structure, vent, and different geological structure were generated by using image interpretation technique. Another one is supervised maximum likelihood classification system. This method was basically applied for classifying both land use, land cover, and lithology classification. And another one is multi-criteria, GIS-based multi-criteria evaluation method. These were applied for lava flow hazard evaluation and for also risk assessment. And different factors are analyzed, and they have done thematic layer preparation for those evaluation using the GIS, ArcGIS software. Within there is one method, so-called analytic hierarchy process, which is classified into categorized into multi-criteria evaluation, and it is a process of weighting factors based on their importance. For the lava flow hazards, different factors were analyzed based on their importance. For example, faults, vent distance, caldera distance, elevation and slope were analyzed through analytic hierarchy process based on their contribution for the lava flow hazard. And for lithology classification, the different lithology were identified based on band ratio techniques. For example, for Wilder tuff, 8:11 and 12:2 band ratio technique was applied. For alluvium, fine sandstone and basalt, 12:3 band ratio technique was used. And for rhyolites and trachyte lavas, 12:11 band ratio was used. And by using by stacking the image, the classification was done. Geology of Fantale and volcanic and surrounding regions. Fentale is known to be a bimodal eruption history, implying there are both explosive and effusive eruption products in the area. So this stratigraphy shows the areas which are deposited during different caldera formation. For example, this is from top to bottom. It shows the oldest unit. This is the post-caldera activities are the younger one, and these are the Kasam basalt and Kasam ignimbrite are associated with plateau formation, then followed by pre-caldera or formation or caldera collapse, Fentale caldera. That are the units which are deposited during caldera formation and post-caldera after the formation of Fentale caldera. This is a geologic map of Fentale volcano. As we shown, as the map shows, the voluminous unit, deposited unit in the study area is Wilder tuff, as we see. This is erupted before Fentale caldera formation and also during the Fentale caldera formation. And also there are lava flows, trachytes and rhyolitic lava flows in the study area, which are erupted from the center of Fentale volcano. And also this Dauphin basalt is not associated with Fentale volcano, and it is associated with 1G fault belt. And the plateau formation units such as Kassam basalt and Kassam ignimbrite look like here, and there are different geologic structures, fault structures here in the study area. This is Fentale caldera and Awash National Park boundary. Okay, the hazard assessment was done based on the theory of uniformitarianism, implying the inactivities which were happened in the past will be the key for inactivities which will be erupted in the future. So the presence of geothermal features such as femoral hot spring and mud pool aligned with normal fault indicators. The area is volcanically active and there is a volcanic unrest in the area. So based on the past eruption history and volcanic products in the area, by combining with those geothermal features, the expected eruption type and potential hazard of the area will be lava flow hazard, having high viscosity, silicic and low viscosity basaltic lava, pyroclastic flow, pyroclastic density current hazard, pyroclastic fall hazard, or tephra fall hazard. Hazard assessment for lava flow hazard evaluation, the geologic features such as fault structures and vent location, those black things and difference are extracted. And this is the hillshade maps extracted from the DEM. So the 5 factors such as caldera, ventus, faults, and elevation and the slopes are evaluated. So there are lavas which are erupted from Fentale caldera, trachytic lava. So as the caldera distance decreases, the hazard increases. So they have inverse proportional. The same for the ventus. As the vent caldera decreases, the hazard also increases because the lava also enter into the surface through the ventus. Fault is also another geologic structure which allows the entrance of lavas into the surface. So as the fault density increases, the hazard also increases. Elevation is the topographic parameter. The lava flows from high elevation to low elevation, and slope is another topographic parameter. The lava flows fast at a steep slope, and it flows slow at gentle slope. This is the factor evaluation map of lava flow hazard. The first one indicates caldera distance, the vent distance, fault density, elevation, and slope. Then, after evaluating those factors, the pairwise comparison matrix was done for those 5 factors, and they was given different weights based on their contribution. For example, for vent location and caldera distance, they was given 0.36 because they both allow the entry of lava into the surface, then followed by fault, elevation, and slope. So by having those this weight, the hazard map for lava flow was done, and the consistency ratio is 0.03, which is less than 0.4. So this evaluation is acceptable. This is the lava flow hazard map of the study area. As we see from the map, the very high hazard concentrated at calderas, because so many vents are adjacent to the caldera, and so the trachyte and rhyolite flows are found in the very high hazard zone. Different elements are exposed for this hazard. For example, there is this Awash National Park is more nearby for this hazard, so it is more vulnerable element. And there is also a railway. This railway and Lake Basaka is also more nearby for the caldera, so they are more vulnerable elements. And there are irrigation farmlands, this Matara sugar plantation and Awash Malka farm in the area. So the more vulnerable element is Awash National Park, as we see from the area. And the very high hazard is classified, and it covers about 10.9% of the whole, the entire area. For assessing both pyroclastic and ashfall hazard, the lithology classification was done. As we see, different lithologies which were erupted during different time were merged as one unit. For example, the both welder tuff of Tinish Fentale and Fentale are merged as welder tuff, and another units were merged, and this lithology classification was done. So the voluminous unit is welder tuff, classified as welder tuff, and there is lava flow products of rhyolite and trachyte. Then the old basalt unit is this one, light green unit, and the recent lava flows, which is called basalt, which are erupted from Tinish Sabobar or tuffring. Pyroclastic flow hazard. This hazard is done. This assessment is done by reclassifying this lithologic unit, and the very high hazard covers about 36% of the area. The red one shows the very high class. Then the yellow, followed by yellow, light green, and green. So this hazard covers more area. So many exposures are vulnerable for the hazards. Another hazard is ashfall hazard or tephra fall. Ashfall deposits are more concentrated or deposited in the northern and southern part of the area. So the two towns, such as Matahara and Addis Ketama, are more exposed for the ashfall hazard in the study area, and the very high hazard spans about 9.7% of the entire area. Vulnerability assessment. Vulnerability implies the probability of those exposures, such as population, localities, and different economic activities, to be harmed by an eruption of Fentale Volcano. So this map is a population map of the study, a reclassified population map. Then locality, economic activity, health facility, different education facility, religious facility, and infrastructures, both road and railway. These are classified as vulnerability to assess the vulnerability of the area. And there is also land use land cover classes. 6 land use land cover classes were prepared for the study purposes. And those 6 classes are reclassified into 4 based on their importance. For example, built-up was classified as very high, farmland and water body classified as high, and forest classified as moderate, and shrub and bearland was classified as low. Risk assessment. The risk assessment was done by combining both hazard and vulnerability of the area. So the hazard was given a very high weight, then followed by population, land use, land cover, locality. Then the other facilities was given the same weight. This map shows the risk of the 3 hazards. The first one is the risk of pyroclastic flow deposit, the risk of ashfall hazard, and the risk of lava flow hazard. As we see from the map, the red one shows the very high hazard class, and the light red shows the high hazard. Then the yellow shows moderate, and The green one shows the low class of the risk. As we see from the map, the hazard which has the highest risk is pyroclastic flow because it is fastly moving and it is devastating. It covers a large area, so it causes more impacts on living things and also different man-made activities. Then it is followed by ashfall hazards, and the last one is the risk of lava flow hazard. So there is limitation of volcanologic data in different parts of the world. So the hazard assessment is done based on quantitative measures, implying the hazard assessment is based on done by using volcanic hazard maps. Volcanic hazard map implying analyzing the hazard based on the past eruption history and the volcanic products in the area. There are different forms of volcanic hazard maps. Geology-based hazard map done based on the different products distributed in the area. Different volcanic hazard studies use GIS in order to model the hazard map and spatial extent of different volcanic hazards according to Felipe. There was a study which was conducted at Mexico by Alcan using GIS-based multi-criteria evaluation. In this study, the volcanic hazard assessment was done for both pyroclastic density current and ashfall hazard. Then he combined the hazard map with vulnerability in order to generate the risk map of the area. And there is also a study in Ethiopia conducted at Aluto Volcano by Mengistu using GIS-based multi-criteria evaluation. So the possible explosive eruption type and hazards from Fentale include pyroclastic flow and fall deposits accompanying dome collapse, ignimbrite forming eruption, Vulcanian or Palean and Subplinian eruption accompanying pyroclastic flow and pyroclastic fall, phreatic magmatic eruption, and partially explosive strombolian type of eruption. So the result shows pyroclastic flow is projected to be higher. It will destruct any buildings in the area, especially in the Matahara and different localities. It will scorch Awash Melka farmland and Matahara sugar plantation. It will kill biome and wildlife present in Awash National Park. It will also trigger a mudslide when it mixes with Awash River. Then another one is ashfall hazard. It will cause health issues. It will also cause respiratory related problems for human beings, and it will also disrupt different infrastructures in the area. Then the lava flow hazard will provide a modest risk as compared to that one. The main two towns, Metara, Addis Katama, Lake Beseka, Awash National Park, and other neighboring localities are more vulnerable for the three hazard types in the area. Conclusion and recommendation. Fentale is stratovolcano which has developed a shallow magma chamber inside, having both explosive and diffusive eruption products. Remote sensing and GIS are used as a good tool to assess volcanic hazard and risk of the area. So the hazard assessment done for the three hazard types such as pyroclastic, lava flow, and ashfall. The pyroclastic flow will cause a very high risk as compared to lava flow and ashfall, and it will cause different impacts on different exposures followed by ashfall and lava flow. Recommendations. The area is geologically active and it is surrounded by different economic activities. So there should be a continuous volcano monitoring in the area. There should be also different investigations associated with geologic and geophysical approaches to reduce the risk from future eruption of Fentale. There must be a detailed hazard assessment to measure the magnitude, the future magnitude of eruption in the area, and the federal and regional governments should collaborate to do on early warning system and hazard management. I would like to thank my supervisors, Professor Gazany and Dr. Biniam, Addis Ababa University, School of Earth Science, Regional Center for Mapping of Resource, for development, RCMRD and James, people surrounding the study area, and my parents. Thank you.
Thank you, Rahel, for your presentation. Questions?
Thank you, Rahel, for this wonderful presentation. Not a common thing to see young youth already talking passionately about volcanoes. I have 2 points on which I would like to seek some more clarification. One, about the sources of your data. You mentioned that you got population data from DivaGIS, right? Yeah, population, DivaGIS. I was wondering, doesn't Ethiopian government hold censuses, like official demographic data, instead of getting such data online? That's one point. Another point is you mentioned in the beginning AHP, analytical hierarchy process, that you used it. I understand that this is a technique used in a multi-criteria evaluation studies to assign weights to factors. If I recall well, you didn't elaborate more on that, how you used that in your study. Can you elucidate how you used this technique in your study? Thank you.
Okay, thank you. I was got population data from other source, but it was not full. It was not detailed. So I am forced to download from DivaGIS. That's why. And the second, I don't understand the second question. Repeat. The second question.
Oh, the second question was about AHP. How did you use that technique in your study? You didn't elaborate on that.
Analytic hierarchy process, or AHP, was done for evaluating the factors of lava flow hazard, which facilitate lava flow. For example, fault, elevation, slope are parameters which facilitate the lava flow hazard. The fault allows the entrance of the lava. So I give a weight for them based on their contribution. For example, for vent and caldera, I gave a higher weight because both allow the entrance of the lava, then followed by fault, elevation, and slope. And instead of risk assessment, I weight the factors based on their contribution as the same as for lava flow, as I do for lava flow. And I give a weight for hazard, a high weight for hazard, followed by population, because based on their importance, followed by land use, land cover, and localities, and different facilities. Okay.
Okay, mine is not a question. I want to add on the first question regarding the population density data. So I think you want the raster data for your study, right? So as I work for the Central Statistical Agency of Ethiopia, so the data we have is not a raster one. So it will not help you here. So it's just a number. And so for mapping purpose, you need a raster one. And that's, I think, why you downloaded from DivaGIS. Yeah, thank you very much.
Thank you, Noe.
Yes, okay, a question. Did you look at the teleconnection between, of course, the volcanic activities and other earth movement processes that might influence or increase the frequency of these volcanic activities perhaps in future?
What?
like the teleconnection of the volcanic activities and other parts of like earth movement. We have the earthquakes. At times they can also cause earthquake, and maybe we know if in future will the frequency of that volcano continuing erupting, or it will decrease and maybe finally become dormant.
Okay, thank you. As I said, there are different geothermal features which are a sign of volcanic unrest, or which shows there will be an eruption for the future inside the caldera and outside the caldera. Specifically, they are found at southern northwestern part of the Fentale caldera. So they shows there will be an eruption for the future. And there are different rupture surface or fissural structures in the state area. So they shows the area is volcanically active.